Okay, so this is problem number 6. In problem number 6, we're asked to calculate the electrical field strength of a microwave if the power density is 15 watts per square meter. Well, let's back up a little bit here and take a look at this. Power density is the amount of power emitted into free space that's distributed evenly over the surface of a sphere as it goes out. As that sphere expands, we have a certain amount of power that's being generated. As that sphere expands, the density of that power diminishes per square centimeter. The density of that power diminishes as that sphere gets bigger. Because as that's, if you can imagine, if it's a small sphere like 1 foot, that surface area that's a foot away, that circle that's a foot away, the surface area of that sphere has a certain area. If we go to 6 feet away from the power source, that sphere is much bigger, so the same amount of power being emitted is now diluted. It's in each square centimeter of that bigger sphere, there's less power density. So we're interested in this particular problem in finding the electrical field strength of a microwave. Its power density is 15 watts per square centimeter. So in this case, we're being given the power density, so we don't have to worry about the size of the sphere that we're dealing with, the area. So for instance here, power over the area of the sphere is the power density. We don't have to worry about that because we're given that power density already, S already. So that's already been determined for us. In this case, this is another formula that accommodates the, if we have a certain amount of directionality, if it's not isotropic, if it's not in a circle, it's not expanding equally in all directions, this formula makes up for that. This is the area. This is accommodations to the directionality and the gain of that particular power, of that energy source. So the formula we're interested in is this formula that associates the electrical or the magnetic field, the strength of those fields, to the power density. Now we're interested in this case. They're asking us about the electrical field strength. Now that makes some sense to us because this is a microwave source, and when we're very close to the source, like literally like a fraction of a wavelength from the source, the primary energy is the magnetic field that dominates. The magnetic field dominates very close to the source. But as we get further into what they call the far field area or the near field area, magnetic field dominates. And as we get further out, say 2 or more wavelengths away, then the electrical field dominates. And you can kind of see that in this formula. The power density is equal to the electrical field squared over 370. In other words, we have to do things to make the electrical field smaller. And in the case of the magnetic field, we have to multiply by something to get it to be equivalent to the power density or relate to the power density. So with microwaves, this is not a surprise that we're doing this in the far field area, because with microwaves, the wavelength is very small. So it's likely that almost any distance from the source, any reasonable distance source, would put us in the far field for very short wavelength radiation power. So let's take a look at this formula. We have another form of this formula here that I can use, which is a little bit easier to see. So I'm going to do this calculation. Okay, and first, let's see, our power density is 15 watts per square meter. Okay, so I'm going to start my calculation. So first of all, number one, if you are just first watching this video, now's a good time for you perhaps to pause, do the problem on your own, and then come back again and follow the solution with me and see if we get the same answer. Okay, so the power density, S, is equal to 15 watts per meter squared, and that's equal to the electrical field squared over 3770. So our units for, in this formula, our units for power density are milliwatts per centimeter squared. So I'm going to have to do some conversion here. So 15 watts per square meter. Okay, so now we have 15 watts that's spread over a square, that's collected over a square meter. I want to know the equivalent power per square centimeter in that. So it's going to be less than 15 watts. So I'm going to take that 15 watts per meter squared, and I'm going to divide that by 10,000 centimeters per meter squared. So the equivalence here is that 1 square meter is the equivalent to 10,000 square centimeters. Okay, and we can prove that here. This is 1 meter by 1 meter. So 1 meter times 1 meter is 1 meter squared. So that same area, 1 meter is equivalent to 100 centimeters. 1 meter is equivalent to 100 centimeters. So 100 centimeters times 100 centimeters to get this area is equivalent to 10,000 square centimeters. So 15 watts spread out over a full square centimeter, we divide that by 10,000. And that now would become, and meters would cancel out, and this now would become centimeters squared, watts per centimeter squared. So now the other part of this is that it also tells us that the power density is in milliwatts per centimeter squared. So I'm going to just actually, for the moment, I'm going to say, let's go ahead and work this out. So if I divide that by 10,000, it's the equivalent of moving the decimal place over 4 places. So that'd be 0.15 watts per centimeter squared. Okay, and we now are going to have to change that from watts into milliwatts. Well, this number of watts in terms of milliwatts is going to be as 1,000 milliwatts in each watt. So I'm going to have to multiply that by 1,000. So this is the equivalent of 1.5 milliwatts per centimeter squared. So now at this point, we finally have our power density in the units that we needed. So that's going to be equal to E squared, the field strength squared, which is going to have the units, field strength is going to be volts per meter, okay, but E squared is volts squared per centimeter squared. Hence, when we take square root, it'll work that out for us, over 3770. So cross multiply. So E squared is equal to 1.5. I'll drop the units for the moment. Milliwatts over square centimeter. I'll drop the units. Okay. Times, oops, 1.5 times 3770. So E squared is going to be equal to, so E rather is going to be equal to the square root of 1.5 times 3770. Let's get the calculator up. 1.5 times 3770 is equal to 5660, and I'll take the square root of that. So E is equal to 75.2, and what are our units? Well, our units are E squared was volts squared per meter squared, so take the square root of that, it's going to be volts per meter. That's our answer, 75.2 volts per meter. So Problem number 7, and for those of you online, I apologize, but I'm repeating myself. UHF microwave systems that are used for transmitting a very large fraction of public telecommunications employ a circular antenna with a diameter of 40.5 inches. We just mentioned before, for those of you that are just listening to the first time, that dimension inches may be problematic when we use the formulas that we're going to be working with. So we're going to keep that in mind. Antennas transmit their information using UHF microwaves that have a wavelength of 46 centimeters. How far do you need to stand from the antenna to be in a far field? And we want the result in inches. Diameter that we're working in inches almost exclusively here. But again, we're going to have to look at our formulas. So one of the things we just discussed is that in the near field, the magnetic field is dominant, and in the far field, the electrical fields are dominant. And the near field is typically defined as areas very close to the source, within a fraction of a wavelength. Far field starts further out. And when I mean further out, I mean 2 or 3 wavelengths away from the source. Some things you may, I think some of the textbooks may say something even larger, but for the most part, the material that we've been using suggests roughly 2 wavelengths from the source. So in this case, just so we have a window in our heads of what the answer to this is, where the far field starts, we see that the wavelength of this particular radiation, these radio waves, are 46 centimeters. So in our heads, we're saying to ourselves, well, it looks like it's going to be around 90 centimeters. But we're going to use a formula to actually calculate what the far field distance is. And this formula is going to tell us the distance to the far field. And let's see what we have here. What do we have here? The radius, let's say it's broadcast. This broadcast is going omnidirectional. It's going in every direction, right? So it's a big circle. So R, it's defining the distance as a radius. So R, far field is the distance from the source, basically, is equal to pi times the diameter squared. The diameter squared in this case is the diameter of the antenna, and divided by 8 times the wavelength of the source. So I got 2 choices here. One choice is to define this entire thing in inches. So I convert anything I need here to inches, from centimeters to inches, and that'll give me a result in inches, or work in centimeters, convert everything to centimeters. So I'm kind of stuck in between here because I got 46 centimeters and I got 40.5 inches. So I'm going to convert it in, last time I tried this, I converted it into inches. This time I'm going to convert the diameter of our antenna into centimeters, and then we'll convert back into inches at the end, just because it's different than the last time I did it. Okay, so I'm going to go to Google, and I am going to convert inches to centimeters. And 40.5 inches is 102.87 centimeters. I'm going to call that 103. You should not round until you get to your final result. Because if you're doing calculations, you're going to wind up squaring something, finding square roots, multiplying by other things. If you round, you have the potential, if you round early in your calculations, you have the potential for amplifying the rounding area that you have. So there's another instances of do as I say, not as I do. I'm going to change this to 103 just to make it easier for me to do the calculation expeditiously. So this is the same thing as 103 inches, right? Yes, 103 inches. Okay, so let's do our calculation. I'll move this out here. So the far field distance, RFF, is equal to 3.14 times the diameter, square diameter of the antenna, which is 103 centimeters, squared, over 8 times the wavelength. The wavelength, 8 times 46 centimeters. Okay, so let's look at our units first. Our units are going to wind up centimeters squared over centimeters. So our units are going to wind up being centimeters. Okay, so centimeters squared divided by centimeters, just centimeters. Okay, so let's actually do the calculation. Okay, so I'm going to do the denominator first. The denominator first. 8 times 46 is equal to 368. And I am going to put that into memory, clear this, and then I'm going to do my numerator. 103 squared is 10,609 times 3.14 is equal to 33,000 divided by my denominator, divide by and recall my denominator, and it comes out to 90.52. I'm going to call that 90.5 centimeters. Okay, so that looks a lot like our expected result. So I feel a lot more comfortable. Unfortunately, it's asking for the answer in inches. So I'm going to go back to Google. And I'm going to ask Google to do the opposite calculation for me. I wonder if I can just do it by typing it in here. Yeah, and the distance is 35.6 inches. Okay, so R is equal to 35.6 inches. You guys on board with me on that? We okay with that? I'm going to pause the recording, assuming that this is still recording now. Okay, if the power output of the antenna described as one in the previous problem, problem number 7, is 0.5 kilowatts instead of the, I think it was 15 kilowatts that we were working with before, or 15 watts or whatever it was. If it's 0.05 kilowatts, what will be the approximate power density in milliwatts per square centimeter produced by this antenna at a point 12 inches directly in front of it? Okay, so, as before, we talked about the near field and far field. So we calculated the distance to the far field in the previous problem, and it turned out to be about 36 inches roughly. Okay, so this 12 inches, we're in the near field. We're very close to this antenna. Okay, so in that case, in order to calculate what the power density is, or that's associated with this antenna, when we're very close to it, we're going to have to choose one of these two formulas. Since we presume ourselves to be in the near field, not in the far field, but in the near field, you could argue that we're kind of in the transitional zone because, well, we're less than one wavelength, but we could be in the transit, whatever. Right. So this is a little bit of a academic exercise here, okay, rather than what we might really perfectly measure. Okay. So I'm not going to use far field formula because I'm not in the far field. So I'm going to stick with the near field formula that associates the power density with the power output from the source that we have. Okay. So what are our units? Well, our units of the power that this is producing, our units are milliwatts. The diameter of the antenna is in centimeters. Okay, again, we have to change it because it was given to us in inches, right? And the power density is going to be in milliwatts per centimeter if we stay consistent with the formulas. So I'm going to go ahead and go back to the problem and actually do this calculation. So here's our formula. So the power density near field is equal to 16 times the power density in milliwatts per square centimeter. The power, the power output in milliwatts. Okay, it's given to us in kilowatts. So 0.05 kilowatts is 50 watts. And 50 watts is how many milliwatts? What's 1,000 times that? So it's 50,000 milliwatts. So we're going to make that conversion first. So we have 50, excuse me, let me undo this so I get a little bit neater. Okay, so it's 16 times the power output, which is 50,000 milliwatts, divided by pi times the diameter squared. Now, the diameter was in inches. I think it was 40.5 inches. If I'm wrong on that, just chime in there in the chat box there, so I'll correct it. Okay, and I'm going to convert again. I'm going to convert inches into centimeters. That's the units that we have to work with. 40.5, and that's 103 roughly. Again, I'm going to round it. Hopefully, you'll avoid rounding at this early stage, and but to make it a little more expeditious, I'm going to round it, and it's going to be 103 times 103. In fact, this is an example, perfect example of where you increase the error, because I'm going to take that 103 centimeters, and I'm going to square it. Right, so now there I just increase the rounding error that I did there. So like I said, do as I say, not as I do. So it's equal to 16 times 50,000. I'm going to go ahead and do the calculation here. So I'm going to start with the denominator first, because it'll make it easier for me to do the division at the end. 3.14 times 103. Oops, let me start with that first. 103 squared times 3.14 is equal to, and this is centimeters squared that we're working in. On top is milliwatts, so our answer is going to be in milliwatts per square centimeter, which is the unit that we're after. Okay, so that's, I'm going to put that into memory, and I'm going to clear the register, and I'm going to do our numerator, 16 times 50,000. Okay, and I'm going to take that and I'm going to divide by our denominator, and I wind up with 24 milliwatts per square centimeter as our result for our power density in the near field, very close to this antenna. Okay, how do you guys feel about that?